Okay, so in this case, I'm just going to go over to the part where it says write an equation that will determine the time it would take a CHP to catch the car. So trying to find a derivation for this, and so if you have this question right here, solving for a variable, and we're going to solve for the time t. Um, Now, if we put these two into what we want to, how we want to try to solve it, the car is going at a constant rate to the right, like this, and the motorcycle is actually going to be trying to catch up. So there's the cop on the motorcycle, and by accelerating, so it's going to go faster and faster. Um, so how do you answer these questions? You have to know equations and you have to know variables. And so remember that the variables that we have that you're going to look at are related to the equations that we have. And we really have two equations. We have on our equation sheet, we have equations such as v, our final velocity, is equal to our acceleration. And on the equation sheet, in the x direction, times t, plus our v naught, which is our initial velocity. Then we have a second equation which relates distance or position. So this is our final position is equal to our initial position plus if we were moving at some v naught initial velocity, we times it by the time. And if we are accelerating, we have to also add 1/2 times the a in the x direction, considering left and right x direction, times t squared. And so those are our two basic equations that we have right off the bat. This first equation doesn't really apply at this moment because although I'm looking for t, I don't know vf, and this is not the right graph. The right graph for this one would be a vt graph, and this one is basically an xt graph, and so here we have an xt graph. So one of the things in order to understand these things is to find out what is the same, because I'm going to have an equation for the car, for the speeder. I'm going to have an equation for the speeder, and I'm going to have a different equation for the CHP. But if I can find out what is the same between both of them, then it can help give me a starting point. So when there's two things that are the same, the two things that are the same is the change in position actually is the same, which is the delta x, but also the delta t is also the same. They have the same delta x and the same delta t. So what I can say about these is I can say that. Now I'm gonna actually leave myself a little bit of space here, and I'm gonna write knowns and unknowns in this space here, but I'm gonna write those things kind of down here, equals and equals, and I'm gonna leave myself a little bit more space to put some more information up here. So what I said before was the delta x of the speeder, and actually I should try to keep my color coding if I can, and let's see how long that lasts. The delta x of the speeder is gonna be, where am I at? See where I'm at now. Delta x of the speeder is going to be like this, is going to be equal to the delta x of the CHP. And also the delta t of the speeder is going to be equal to the delta t of the CHP. Okay, so then I want to say, okay, what equations would help me with these things? So in class, I try to make you kind of like painfully go through the motions of finding this stuff, and sometimes that's good, sometimes that's bad. I'm going to be more direct here. So if we look at the two equations, of course, we have this one, and that equation is not the equation that we want to use because it's not the one that's involved with the graph that we're talking about. And then we have this graph here, and really what we're talking about here is, I'll go to right there, is these two equations, this one here and this one here. And more directly speaking is That's the only equation. Okay? Now, when I say that's the only equation, this section, which has no acceleration, turns into this equation. And the reason it turns into this equation is because if that is zero, you get rid of that and you get this equation. And the reason that's important is because that's the equation that we get for the straight line part where there is no acceleration. But that is the equation that we get for the curved part where there is an acceleration. So let's take these two equations, just this one, back to the other page and see how that helps us solve this question pretty easily. So I'm going back to my drawing, and I can say that this equation off of here is the y equals mx plus b equation. Now, that equation actually on your equation sheet is the full equation, which is x equals x naught plus v naught t plus 1/2 a in the x direction times t squared. And then the same equation applies here. X equals x naught plus v naught t plus 1/2 a in the x direction times t squared. I actually should call this, instead of a in the x direction, I should call it a of the CHP. And in this one, I should call a of the speeder. I almost made a mistake on that. A of the speeder. Okay? So knowing this, there's a couple things I got to figure out before I can continue on. Let's start off with this guy. If I move this to this side, right, this actually becomes x minus x naught, which literally is just saying we're talking about delta x. This being 0, delta x is equal to xf. So anyways, another way to look at that would be to write it like this. Delta x equals x minus x naught. So if I move this back to the other side, it will give me my displacement. My displacement is what I'm looking for. How far am I going? So how far am I going is this. VO, I really don't know what that is. I know it's a slope right here. And I also know that it keeps the same slope the whole way through. So I'm just going to copy this and this down. This is the VO of the speeder. I'm going to put a little s on it, and times t. And then I have this whole thing right here. Now, what is the acceleration of the speeder? And the acceleration of the speeder is 0. So if I make this 0, that goes away. So literally, this is the whole equation for this line. The displacement is equal to v of the speeder times time. That's the whole equation for displacement. Okay, on this side, I'm going to do the same thing. This I'm going to bring over to this side, and I'm going to call it delta x because that is my displacement. Plus, well, what's the initial velocity of the CHP? If you look here, you're supposed to get that he's going fast at the end, and he's speeding up from 0. So your v naught of the CHP is supposed to be 0 meters per second. As the story goes, speeder passes him by, he sees him, he floors it, he's trying to catch up. So this, in this case, is 0. In that case, the acceleration was 0. In this case, the v naught is 0. So do I get? I say my displacement is equal to, I'm not sure why I put a plus sign there. My displacement is equal to just 1/2 times the acceleration of the CHP times t squared. And so now, if I look at this, I can solve for these pretty easily by setting one thing equal to the other. Okay, I'm going to do something different in this than I asked you. Then I'm not going to solve for t. I'm going to solve for x in this case. I'm going to say, what does delta x equal? So if I want to find what delta x is equal to, I got to somehow get in there, and I got to have an equation that has delta x in it. So what I'm going to do is I'm going to change this to t equals, and I'm going to change this to t equals. So if I do the math for this, and I solve for t, because what I'm going to do is I'm going to set t equal to t. So if I do this, I get t equals the change in position over the initial velocity of a speeder on this side. And on this side, this is a super common thing. If I'm solving for t, the way you solve for t is you're going to times 2x, right, on both sides. So I get 2x, and it's actually 2 times the displacement. And then I divide by a, so a will go over here on the bottom. And then I have t squared. So I square root both sides, and I get t equals the square root of 2x over a. T equals delta x over v. Okay. I ran right off the page, didn't I? So when I solve this for t and I solve that for t, I get these two different numbers. Going back to this. If my time of my speeder is equal to the time of the CHP, then I can just take this phrase right here and I can substitute it in for TS. Delta x equals delta x over v of the speeder equals, and I'm going to substitute this part on this side, square root of 2 times delta x over a. And now I got to solve for delta x. I'm solving for delta x equals. Okay, if I'm going to do this, I got to get all the x's on one side. Well, the first thing I got to do is I got to square both sides, because if I square both sides, I'm going to get rid of that square root. So I'm going to square both sides. And if I square both sides, I'm going to get delta x squared over vs squared equals 2 delta x over a. Okay, now a little process. I'm trying to get x. Now, if there's 1x on this side and 2x's on this side, if there's 1x on this side and 2x on this side, I can literally just cancel 1x on this side and cancel 1x on that side. So I'm going to get delta x equals delta x vs squared equals 2 over a. And I'm almost done. So now I'm going to times both sides by the velocity of the speeder squared, times both sides by the velocity of the speeder squared, and I'm going to get delta x. Delta x equals 2 times v of the speeder squared over a. Now, if I put this back into my original equation, if I was to get, I could even like substitute any numbers that I want to make up. I could say, oh, the a of the cop is 4 meters per second, and the original velocity of a speeder is 10 meters per second. I could plug those numbers in and then kind of backfill, and I could check myself with actual numbers. Now, that's not the numbers perhaps that might be given on the test, but it is a way to check yourself. So that's a way to solve for the distance. Now, how would you solve for the time? If you want to solve for the time, you would do the opposite. So I would go back to here, and if I'm solving for displacement, right, I want to, if I'm solving displacement, I want to keep displacement in the equation. So displacement is still in the equation here. Displacement is still in the equation here. And I got rid of the time. But this time I want to solve for time. So now I'm going to get rid of the displacement. So the way you would do that is you would say the same thing. You would say, and I can finish off with this, you would say that the delta x is equal to the delta x. And then you would write from your original equation. What is my delta x? Is just v times t. So I come down here and I say delta x is v of the speeder times t equal to, what's the delta x on the CHP? So look over here. The delta x of the CXP is just 1/2 a t squared. Pretty easy. 1/2 a t squared. And then now I would solve for t, and I will let you solve for t. So notice the x is gone. I got rid of the x, but I still have the t. So in this case, I'm going to solve for t equals question mark. And there's some math here. I have two t's, right? So if I have two t's just the same way as before, one of them can cancel. So I cancel that one, I get that one, right? And hopefully you can continue on from there. I don't know. Should I show you the answer? I'm not going to. I'll let you continue on for there. Hopefully you can do that. Okay, anyways, that's just if you were struggling with what we did in class today.